data look like, right? So uh, first we'll just take the first 9 variables. Okay, first 9 columns, variable in the sense columns, right? So for a data set, all the columns will generally, what happens is all the variables are saved as or feed as column vectors, and the x-axis, sorry, rows, all the rows are number of samples for that variables, right? So first entry will be having multiple different values for each and every variable, and variables will be constant. Okay, the the data you collect of the variables will be constant, right? Just the number of entries will be different. Okay, so that will go along the rows. Okay, so first we'll take first 9. Okay, let me just show you how the data looks. Right, yes, 339, 336, 9, and 10. So last one is your classification, sorry, categorical variable. Okay, and the rest of the 9 are numerical variables. So first we'll import the first 9 columns or variables and assign it to X. Okay, then we'll see how the X looks like. So it will be this all the it will be same as the data set, just the last column of class will be removed from this data set. Okay, so this is how your data looks. There are 106 rows, that means 106 samples are there, and 9 columns, 9 variables are there. Okay, okay, now we want to resample the data set. Okay, so you might um, why do we need to resample the data set, right? So first that we need to know. So resampling is done so that you can show that the data is the model is not dependent on the order of your data set, right? So that thing can be eliminated by the resampling of the data set. Okay, so the pattern breaks of the input data set, and we can see whether the algorithm is affected by that or not. Or another thing is, when you are having some less number of data, right, then you will need to resample your data set, rearrange your data set, right? And then testing and splitting will be done so that um, your input will be changed, right? So testing and training, what is testing and training and why do we use it, that we'll see in the further down the lecture. Okay, but for now, understand that resampling is useful for changing the input variable, right? Input of your algorithm. Okay, so resample, we have imported the function of resample from the sklearn utils library. Okay, that we'll use now in here. So resampling is done, number of sample is equal to 200. Okay, and random state is equal to 0. So what will happen, that whenever you are doing some iterative process, okay, so you need to fix your initial point, right? Beginning of your operation, you need to fix that. Okay, say you are generating random numbers in the any any system, right? Let's say C or Python or any system. So what will happen, that if you don't fix the initial point and generate data randomly multiple times, right? So for the first time, let's say you are generating 5 data points randomly. So if you run this, then for the first time, the random the 5 numbers will be different. If you rerun this same command, then what will happen, your numbers will be changed, right? So that will be difficult or not convenient for you if you are just reperforming the experiment, or you are explaining it to someone, right? Or let's say you have stored your data set, you have worked on a, a data set, particular data set, right? you have used some random numbers in that, and you have stored that file. Right now, let's say you want to you are working on that file after the system is shut down. So if we just restart the Jupyter notebook, for the case being, so if you just restart the Jupyter notebook, you will see that the operations, you each and every command you need to perform um, as a fresh start, right? So if you run this command of random numbers, so it will generate new data set. Your output will be changed, right? So to avoid those scenario, you will just need to fix your initial point where you started while you were iterating some process, right? So that you can do with random state is equal to, okay, so you can just write any number in here, right? You can assign any number to random state, it doesn't matter, but you need to assign some numerical values, right? So that whenever you are reperforming the experiment or reperforming the rerunning the code, the same numbers or random state will be generated, right? So that is why random state is important. Now x is our variable that we have extracted from the beat issue data set, right? Okay, so we are assigning it to z and printing the z, right? So we have resampled the x data set and assigned it to z. So if we just print this, you will see that the numbers are there, right? If we just compare it with your x data set, so first entry was 524, second was 330. So if we just compare these two, you will see that the first entry in here is different, right? It is not 524 and second entry is not 330. Okay, so what is happening here? So data is resampled. Okay, the data is resampled here. So your first entry is not what it used to be earlier before resampling, right? So but the good thing is that you have index number in here, so you can compare, or you know that on which row my first entry is, right? For z it will be different, right? For z first entry is 44th, but this 44th row is of x, right? If I just print the x of 44, you will see that I'll get the values of 172. So I owe my first variable of x at 44th row was 172, right? So that is 172. Then PA 500, that is 0.127, right? Okay, 0.127. Then HF, that is your 0.038. So the row will be same, but it will be just rearranged in your new data set. So that is what resampling is. Okay, so anybody has any doubt up till now? Okay, then we'll assume that nobody has any doubt and move on. Okay, so what we were talking about, the testing and training data set. So first we'll import the sklearn library. From that sklearn library, we'll import the sub library of model selection. Okay, from model selection, we are importing the training and train test split function. Okay, so what it will do? So train test split will split your data set into different parts. So one part will be your training data set and second will be testing. So that will be this will be operated randomly. Okay, so it's not that your training set will be your first 500 entries, or testing set will be the rest of the data. It will be assigned randomly. Okay, so the new data that is generated, it is generated randomly from your previous original data. Okay, so first we are importing the data set beat issue into data variable. Now if you just call for the shape of your data, then you'll see that there are 106 rows and 10 columns. Now this is how the train test split command looks like. So first you will start with train test split, then the data set name. Okay, we have used the name of variable or data as data, then we are giving it as data. Okay, if you have any other name for your data set, then you can type it here. Okay, next, the test size. So test size will be like, let's say you want to train your model on the basis of 50% of your data, and the rest of the 50% will be your testing set. Okay, so first you will train your model. Okay, it will be like your exam, right? So there is one manual. Okay, professor is having a manual. Okay, he has around 100 or 500 questions in his manual. So what he will do, he will take few number of questions from each of the chapter, or you can say topic, and he will teach you, right? So the similar thing will be happening with your machine learning algorithm. You will be taking a data set, a chunk of data set, and then training your model on the basis of that data only. Okay, and next comes your exam, right? The professor has teach you or taught you something in his class, and he will take exam, so that uh, he can evaluate whether how much or to what extent you have learned from his class. Okay, so that we can do with testing in our machine learning algorithm also. So first he has given you some data, that will be your training. Okay, so training questions were given to you. Now testing questions will be there, that are not included in the, so both will be exhaustive data sets, right? Exhaustive sets. So there will be no, you can say, common part. Okay, training and testing data will be having no common part, or no similarities between each other. Okay, so in here we have given test size is equal to zero point 0.3. That means of 100 data points, we are giving, we are excluding or taking part 30 data points from the data set, and we are keeping it as our training set. Okay, so the rest of the 70% of your data will be your training set. So you will be training your algorithm with the 70% of your data, and 30% will be used for training, testing the model or algorithm. Okay, now the next, you can see the random state 1 2 3. You can assign any number in here. Now, and there are two things: data train and data test. Okay, so in here we have divided the data into training and testing data set. So there will be two parts, right? First will be your training set, and second will be your testing set. So that you have to keep in order. First will be your training data set, and second will be your testing set. Okay, if you just run this and now call the length of the data train. So data train is your training data set. Of that data set, how many entries are there that we can call from? So first we'll, so original data was having how many? 106 entries, right? And the training data set is having 74. So that will be approximately, I guess, 70%, right? 106 multiplied by 70. So that will be almost around 74. Okay. Okay, then, so that was our training data set, and this one is our testing data set. So if we just check the, okay, so that will be 32. Okay, 76 and 74 and 32. So next, so this one is print train data set. So that we have done earlier. So there are 10 columns. The columns are as it is as per our original data set. The data set was data, right? So that is having the last column also. In here we have excluded the last column from the data set, so that we, so it was another variable, right? The values were assigned to another variable, that is x. We have taken our data from data set. Okay, data set named as data. So where did it, okay then training data set, testing data set we have called. Okay, so next will be k-fold. So if you have to just simply understand what is k-fold, then you can take it as, let's say you have a data set of 100 points. Okay, we are having a data set that is having 100 data points. Okay, now you what will you do? So let's say in the one set, for first time what we had done, we have divided into training and testing data set, right? Training and testing data set for the first time. So in that case, the whole process is random, right? So the whole process is random. So what will happen, the data will be in the training data, the data points will be selected randomly, right? Now, so this one will be your first set of values, right? First set of values of training and testing. So that will be your first fold of data. Okay, so now again you are doing the same training and testing on splitting, training and testing splitting of your data for the second time on the same data set, right? So the process being the random, so the process being random process, so what will happen, the next time the training data will be different and testing data will be different compared to the first time, right? So now first fold or first set of training and testing data will be different from second time, second training and testing data set, right? So there will be minor changes. Let's say you are having lesser number of data points, then you will see that there is commonalities between these sets, right? But when you are having a large data set, then there will be lesser number of common points, right? Just a second, I'm taking a pause, just 2 minutes. Okay, sorry. So okay, we were on the key fold, right? So key fold is like you are performing training and testing splitting multiple times, right? So there will be, let's say, you are splitting the data set into 5 parts. Okay, the whole data is divided into 5 parts. Okay, so the previous example was uh, just to inform you that each iteration will perform a different training and testing data set. So if we just perform or let's say split the data set into 10 parts. Okay, so now you will be having you can have multiple input, but there will be only sorry you will be having, you can have like you have 10 different sets. Okay, that constitute a original data. Okay, so let's say you are combining first five part of your data set and the second 5 parts of your data set. So that will be splitting of 50-50, right? So first 50 will be your training set and the second 50 will be your testing set, right? For the I guess up to the till this you understand what I'm trying to say. Now let's say you are taking 6 part out of your 10 parts of the data set. So 60% will be your training set and 30% will be your testing set. Okay, now if I just reshuffle all the parts and again take 5 parts. Okay, I'm keeping the training and testing split ratio as 50%. Okay, so 50% means 5 parts and 5 parts, 5 for training and 5 for testing. Now if from the 10 parts I am reshuffling all the parts and taking 5 all as a new start. Okay, so that 5 will be my training set and the rest of the 5 will be my testing set. Now I am again reshuffling the whole 10 parts, right, and taking new 5 parts from the data set. So it may be like that you will be having 2 or 3 parts common with your previous iteration, right? So this is what K folding is, right? If you have any doubt, please let me know. I can explain it again, or we can just move forward. Okay, then. So okay, so this one S. Okay, from sklearn we are taking the model selection sub library. Okay, from that we are importing the K fold, then H names, that is for column names. Okay, you can write anything in here, header names, column names, or ABCD, right? But the values that you are assigned to, that should be matching with your number of columns. Okay, so let's say there are you are having 15 columns, then in here there will be 15 strings, okay, assigned to each column. So this is what we are doing in here. We are giving names to the columns. Okay, so first we have Indian diabetes data set. Okay, and for for that data set we are giving the names. Column names are given by H names variable that we have already performed here. So a new data frame will look like, okay, we can just compare these two things. Okay, so the data set was already having the column names, but just to make sure, we had given, let's say you are having data set that is not having column names, that then you can do it with this command. So the data was already having the column names. Okay. So it has taken the first row, okay, your header column as a variable. No, sorry, entries to your respective variables, right? Now next, data frame dot values. If we just convert it into an array, so it will just look like this. So first is your the again the data frame is this will be your expected output, right? The number of uh, values or entries are converted into array. So array will not be having headers, right? If your data set is having header, right, whether your data set have header or not, sorry, column names or not, the when you convert it into array, it will not be having the column names in here. Now let's say you are having, if we just reverse it back, then if you are having an array and you want to convert it into data frame, then you can convert the number of entries into a data frame, but then after that you will need to perform this command, right? So you are having this array and you want to give this. This is how you convert the array into data frame. Okay, I think something. Now the data set has been converted into the, you see, the array has been converted into the data frame. Okay, so I guess I think something I'm not getting it here right. Okay, we'll see how to add the data column names. Okay, I guess I'm missing something in here. So we'll see how to add the column names to the converted data frame. Okay. Now the next thing that we are calling for the, from the array we are calling the values. Okay, and this is how the first 9 entries will look like. And so the last one being your output variable. So that is y. So the y has been converted into 0101. So this is from the categorical variable. It has been converted to the numerical variable. Either you can type the last variable index, or just you can. So it will give you the same result. Okay. Now I guess k-fold sir has not explained to you. Okay. in detail. So we'll cover it in next lecture. For now, we'll start with linear regression. Okay, so that you are familiar with the regression part. Okay, theory. So first we'll import the data set, then we'll see how the data set looks like. So this will be the your data set. For first four entries will be something. I guess this is space shuttle data set, Challenger space shuttle. So, okay, you are familiar with with the data set, right? Information is provided to you. Now the next, import the matplotlib library to run the to draw the plots. Okay, now this ma- this line is used when you are calling the output. Okay, output in the sense chart, right? Only the charts. You just want to print them in between the command cells, right? Then and then you will need to use matplotlib. But in Jupyter there is no need to run this code, right? Because in Jupyter you will see each and every graph, whether it is a graph or any another variable type of data, any another output. So that will be shown you immediately after the command cell. So you can avoid this, or you can use it. So it doesn't matter in Jupyter now. So first we have taken the o-rings failure, right? First variable, that is. So we have taken the first o-ring failures variable. Is it clear now? Serious? Okay. So did you guys miss something, or shall I continue from this? Repeat. Shall I continue or repeat some part of? Okay, from what part? From K fold is all right, right? All of you get. Did you guys get the K fold or not? Okay, okay, thank you. From linear regression, right? So we are using the Challenger space shuttle data set. You are familiar with this data set. Okay, sir has given you some details regarding this. So we'll just import the data set. Okay, then we'll see how the data set looks like. So there are 5 to 4 entries, right? 5 variables are there, 4 input variables are there, launch IDs are given there. Let's say there are multiple launch were there, and in between somewhere there were failures. So what caused the failures, right? So there are multiple failures are given in here. Let's say there was some problem for temperature or pressure or o-ring failures, right? So okay, so we are just looking at the data set in the challenger.head. Now next we'll take the matplot library, import the library. Now next, uh, okay, matplotlib inline. So this command is used when you want to see your output in between the command cells, right? So this is helpful for this is generally used for rest of the IDs, right? For Jupyter Notebook, this is of no use, I guess, because you'll see all your outputs after each and every command cell, right? In Spider, the output is shown into a different window, so that is why that matplotlib inline is used there. Okay? So in Jupyter Notebook, whether you can use it or not, it doesn't matter. It gives you the same output. Okay, so that is matplotlib inline. Now next one is we are importing the data set. sorry, we are importing or assigning a variable. Okay, the values from o-ring failures of challenger data set are assigned to o-ring failures variable, and temperature is assigned to temp. Okay. Now next, let's say we want to plot o-ring failures and temperature. So whether there is any relationship between these two or not. So first, plt dot why plt, because we have imported the whole library as plt. Okay, so that is why we'll write plt anytime we use the functions from that library. Okay, so plt dot plot will give me a scatter plot. Okay, and there is o, so that is how you get the dots here. Okay, rounded dots. Now if I just run this, you will get similar plot. Okay, so there are discontinuous values, discrete values are there. Okay, so for o-ring failures, so there is 111 and 2, and these are the zero values. For temperature, different values of temperature. Okay, so this will give you a plot. This is how you can see, let's say specifically you want to plot or draw a plot of two variables, and uh, just want to plot these things and get a visual idea how the relationship between those two variables is. So that you can do with plt.plot, because visual data is always better to interpret and understand than numerical data, right? So that we can understand with this correlation. Okay, so for challenger, for the whole data set we are computing the correlation. Okay, so this correlation will be your Pearson correlation. There are two correlations, Pearson and Spearman. Okay, but this one will corr will give you uh, Pearson correlation between all the variables that are present in the challenger data set. Okay, so first o-ring ct, with respect to other variables there is no values. Okay, so there is no relation between, I guess there are values are missing in between this. Okay, so there is no relation, or either the oct o-ring ct. Okay, just take a look. So there are missing values are sorry, only six values are there, right? So this o-ring ct is a unique variable, sorry, constant variable, so it is having only a single value. So that is why the relationship in here is not available, something right missing. So for rest of the values, you'll see that o-ring failures with o-rings failures is 1. For temperature with o-ring failures is 0.72. So you guys understand what the negative and positive values of correlation means, right? You're familiar with this thing, so we can move forward. So let's say values will give you a positive relationship between these two variables, and negative will give you negative relationship that is inversely proportional, right? So if two variables are related to inversely proportional measure, then relation, then it will those two variables will be having negative correlation value. So the more far or farther you are from the zero value, the relationship is strong between those two variables, right? Whether it is positive value or negative value, the farther you go from zero, the stronger your relationship between those two variables is. Okay, so okay, obviously the same variable will be having with uh, exactly this perfect relationship with self. So that is why all the diagonal variables diagonal in here will be having one value. temperature and o-rings is having negative value, that means both are inversely proportional and 0.72. So that is, you can say, decently far from 0 and close enough to 1, so that implicates that both o-ring failures and temperature values, these two variables are having a strong relationship between uh, those two variables are having strong relationship but inversely proportional. Okay, so if whether o-ring failures if we increase the temperature, o-ring failures will decrease. Okay, values of o-ring failures will decrease. Now we are computing the mean value for o-rings, so that is just given in here. Now next is we'll use the stats model. So it will give you, I guess, most of the uh, state models will give you some statistical analysis, right? So linear regression is also a part of statistical analysis. Okay, so from this library we'll import lin- linear model, right? So first we need to import the library. Okay, so that we have done with import.api as sm state models. Then ols is ordinary list square method. Okay, least square method, that is one of the techniques that we used on the back end to generate a linear regression model. Okay, so that will so it is not a big thing. Just what it will do, the least square method, it will take a mean value of your data set. Okay, you have a data set, it will compute the mean, and then uh, it will calculate the difference between each and every value with the mean. Okay, so it will find the difference between first value and mean, second value and mean, third value and mean, and sum all these differences and square it. Okay, so this is what will give you the error between your data points and mean value. And on the basis of that, the slope of a line, or you can say a line, is fitted on this data set, so that the difference between mean and each of the points on that line is very less. Okay, so that is what least square method is. That's an overview, but if you are interested, you can just google it and find out what the least square method is. It's a very easy one. Okay, you can understand it easy, very easily. Okay, so next we have taken the o-rings failure variable and temperature. Okay, so that we had defined earlier in here. Okay, o-rings temperature and temperature, o-ring failure and temperature. These are the two variables that will be used for generating a linear regression model. Okay, so the two variables are given in here and dot fit. Every time we use or generate a model, okay, so for that we will be using variable. Okay, a data set, you will be using the data and fitting that data on a model. Okay, or you will generate or develop a model that will fit the data in the most possible way. Okay, for generating model you will be using sm.ols state model from ols function from states model. Okay, and fitting that model on this data set. So fitting a model on a data set, that means if we just take a simple example of line. Okay, uh, a straight line. So you all know the equation of straight line, right? So that is y is equal to mx plus c. Okay, so in here, let's say you are having y and x. Okay, so you have input and output, x being the input. So if you are plotting a line on a graph on xy plane, so if I just give you x and y value, you can just put the dots on the plane, and uh, a line joining this point will be your you can say model, right? Okay, but you don't have y. Okay, you want to draw a line, but you just only have input value. So input value being your x, you have the value of x, but and you don't have the value of y. Now you want to plot a line on xy plane. So what you will be needing, you don't have y, but you want to plot a line on xy axis. So y is equal to mx plus c. So you will be needing m, x, and c. These three values you should be knowing to calculate the y. Okay, so m being your slope of the line, and c being the you can say intercept, right? C being the intercept and m being the slope of your line. So x you already know. So these are the two variables that you need to compute based on your data set. Okay, so computing those two values, okay, m and c, that is what model fitting is. Okay, so in here what you are trying to do, you are having the x value and y value, and on the basis of those value you are computing m and c variable. Okay, you are determining the m and c variable, so that when I give you only x value, and you can plot the line. Okay, so that is what model fitting is exactly. So you are in here you are computing the unknown variables. Okay, first, okay, I have fit the model on the data set. Now if I just run the summary of the model, okay, so this is what a model looks like, right? It is pure statistical, right? So there are dependent variable is your o-ring failure. Your model is, what was that name, ordinary least square. Okay, ols, your model is ols. Your method is least square. Your timing is given there, number of observations, degree of freedom of residual, degree of freedom of model, then covariance type. Okay, then r square value and adjusted r square value. If you are familiar with the statistics behind the linear regression, then you can interpret, or you know the hypothesis of a data set, then you can understand all these things. This is very helpful for that part. Okay, the f statistics and probability of f statistics. Okay, but for now just take a look. This is what your coefficient and standard error is. Okay, the higher the standard error, the poor your model is. Okay, so standard error is nothing but you have drawn a line with your x and y axis, right? And you are having some points that are far from the uh, respective point on that line. Okay, so the error, that is what standard error is. Okay, so there is function for, sorry, there is formula for computing the standard error that you can refer to. Okay, so this is what the linear model will look like. Skewness, kurtosis, this will give you the idea about the skewness of your distribution. Now the Seaborn library that we have seen yesterday. Okay, you can use the Seaborn library to generate the pair plot. If you just use run this, you'll see this 4 cross 4, 5 cross 5. Okay, so these are the 5 variables, and the pair plot for each of the variable. So you can see that CT value is constant for each value, each variable, right? Pouring city is having only one value, that is 6. In here also you can see that the frequency plot histogram is given for each variable. Okay, and the relationship between each of the uh, with the respective variable is given there. Okay, so if we were looking at o-rings failure and temperature, okay, so temperature is this one. Okay, o-rings failure and temperature, if we just look at this, so this is how the scatter plot will look. Okay, so you can see the data points are very few in here, so that is why we cannot identify any pattern, or the distribution of data is in such manner that there is no clear relationship between any variables, any two variables. Okay, you cannot see any relationship between two variables. Okay, so that is between launch id and temperature is there, but that's not very clear. Okay, so this is how the pair plot will look, and you can compare or analyze these graphs and identify the relationship between these variables. Okay, so next we'll see the correlation that we have seen here earlier. Okay, so in here for each and every variable there is correlation is computed. Now next is the SNS Seaborn library heat map. Okay, so this will give you a very, you can say, representative and interpretable result. Okay, so there are the relationship between two variables is color coded here. Okay, so one being the lightest white color and the dark being the negative one. So that will give you a inversely proportional relationship. Right, so temperature and O-ring failure are having very inversely proportional relationship between these two. So that is what O-ring temperature. Um, okay. Then for brighter colors, you can see the pressure and launch ID. Pressure and launch ID is having positive relationship between these two variables. Okay, so that will be somewhat around 8 or 8.5 something, right? And rest are not having so any clear relationship between any of the two variables. Okay, so that was it. So now we'll take the variables from the challenger data set temperature and assign these variables to x and y. Okay, now this one is a very useful or handy command. You will be facing uh, frequently this type of error, that you might be having your data in different shape, right? Let's say, okay, you are having data set in different shape than expected, then there will be some errors. So you need to convert those data sets or reshape those variables into different shape, right? So that you can do with reshape command. Okay, so just put a dot after the array and it will be converted. So minus will justify that you don't know how many how many rows are there, right? But you know number of columns. So either you can convert your data set into single column vector with this, okay, or you can, let's say you want to convert this variable into a row vector, so that you can do it with 1 comma minus 1. Okay, and if you just want to convert or generate a data set variable that is column vector, so that you can do it with reshape dot minus 1 comma 1. So this is how we have reshaped the data. Okay, and we will use it for training and testing. First we will split the data set. Okay, so we have seen this earlier. Now in here you will see that there are four values. Okay, I think, okay. So this we have understood what each and every entry means. So in here, so only difference is here is that there are two data sets, okay, or two variables. Earlier we saw only one data was there. Okay, so that is why in here there is training and testing. Only two output were there. Okay, but we are giving two inputs in here. Input data are given, there are two data are given in here, and that those data are split into four parts. So first one will be for X data, second will be for second data. So for both the data sets, training and testing will be given. Okay, you should keep that in mind that the order should not change. Okay, so first one will be for training and testing, and whatever data you have assigned here in the first place, that those two will be in here. Okay, so you cannot write just X train and Y train and in that way. Okay? No need to print this X train, Y train. We can just compare the shapes. So you will see the X was having 23 entries, X train is having only 13 entries. So the ratio is 60 to 40. We can use another library. sklearn library is most frequently used when you're using machine learning algorithm. So most of the algorithms are stored in this library. So this is a standard, you can say, general process of using the linear model, linear regression, so that you can use sklearn library and import the linear model as LM. Now we have we have assigned or specified the model as LM dot linear regression. From linear model, we are using the linear regression, okay, and that is assigned to a model variable. So now on we will use linear regression as model. So that is why while we are fitting the X and Y training data set on the model, we are using model dot fit. Either you can use the whole this whole line you can use in here in place of model, or you can use the shorter version with model. Okay, so we are fitting the data set with the model, the results is in here, and when we run this, okay, first, okay, we have imported the assigned the variables, then reshape those variables, train and test. We have fit the model on X train, Y train, and computed the score. That is our accuracy. So accuracy of the model is somewhat around 50%, right? So we can predict our output on the basis of this training data set, okay, and predict the output 50% of the time correctly. Okay, so that is what accuracy means here. And the slope, that was mx plus c. Okay, so that you can it's, there are multiple output or results you can get from here, from the model dot score or model dot coefficient. Okay, so there are different alternatives you can use from this result. Okay. Now next you will see prediction is equal to model. So now we are predicting the y value for testing set. Okay, so that will be our prediction. So this will give us the prediction, and you are already having the y test. So what should be the right value and what you have predicted? So that is what these two things means. Okay. So first one is what should be the correct value and what you have predicted. So these are the two things based on which you can calculate or accuracy or slope of your model. Now we are just plotting this to output so that we can compare whether how the output is accuracy is, right. Now for all the zero values, okay, y test was what, our true values, so there should have been 000, okay, and in here also there should have been zero values. So for a true value, our prediction should have been zero for all these points, but it is giving us multiple values, right. So that means this all of these values are predicted wrong, okay. So this is what it means. Now next, for y value of true value, there should have been one value, okay. So this y should have been, prediction should have been 1, but it is giving us somewhat around zero point 0.3. So that is what our error is, zero point 0.7, okay. It should have been 1, but it is giving us zero point 0.3. So this big our error looks like, okay. So in here also the true value should have been 2, but the value predicted is somewhat around 1.4, I guess, okay. So that is what our error looks like. uh, you'll see how the error will be shown in here when there are multiple values or multiple data points. You can predict, you can call the prediction values from the predictions, okay. Next, let's say we are giving a new x, okay, and on the basis of that we are asking the model to predict our output value for x new is equal, okay. So we are giving a new value to our data set or model and asking it to predict new value for that, okay. So for x new there will be some y new, but we can move forward with this model dot predict only once we approve that the model that we have generated is accurate enough. But accuracy of our model in here was point 0.5, right. So this is 0.4966, so this is what our accuracy was. So 50% accuracy is nothing. You can say, let's say there are only two answers to a question, so you will be 50% of the time you will be true. Let's say you are saying that so there are 10 questions that has been given to you, and you have to answer it in true or false. So if you write all the sentences as true, so that will give you 50% of, let's say there are five questions that are true and five questions are having answer as false, so you will be 50% of the time you will be right, okay. So 50% accuracy is not a big deal. So let's say generally what happens is it whatever north of 80, okay, more greater than 80% is decent accuracy, okay. So we can't use the model to predict or put it in an application. Okay, then this is uh, this is how the linear regression will be done, okay. Now, okay, I guess this is it. We have covered everything into linear regression. Okay, there are two ways we can use linear regression. First one was Stats model, okay, Stats model library, and the second one was sklearn library in here. Okay, then. So this is what linear regression and k-fold means. K-fold, we will see the k-fold thing in the next lecture, or either it will be covered in the theory portion. Okay. Okay, then I'll submit an assignment for you guys on the classroom. You can do it on your own. Thank you.